Okay, now we can look at calculating electric fields for different kinds of charge distributions. We found in the last video the simplest charge distribution is just the electric field of a point charge. So if we have a point charge, we know that the electric field is radially outward. We haven't talked about a lot of the rules for these lines yet, but we know how to calculate this kind of electric field. And here's what we would say. And let me say it a little more specifically this time. The electric field at point P, okay? And I could even call it, let me just call this R. The electric field at R is equal to KQ over R squared in the R hat direction, okay? And so that's for one point charge. If we have a collection of point charges, let's say we have Q1, Q2, Q3, Qn, the electric field from a collection of point charges, again, at some arbitrary point R, okay, is going to be, now this is a little bit more complicated, all right? The electric field at point R, because each one of these things, each one of these charges is at a different R. We have an R1, we have an R2, we have an R3, right? And we don't actually care about any of those. What we care about is the distance from R1 to R. And this distance is actually R minus R1. And the distance, let's say, from R2 to R, this distance is R minus R2, okay? And so what we're looking for then is the electric field at R, and it's going to be, let's take the first one, K Q1 over the value R. In fact, I don't need to put absolute value marks because this is squared, so it's just R minus R1 squared in the R. And now I have to write this as like R minus R1 hat direction. That's so weird, but that's what it is. And then I have KQ2 over R, minus R2 squared in the R minus R2 hat direction. Yeah, plus, and it just keeps on going. So basically it's the sum from I equals 1 to n k q I over R minus Ri squared and R minus Ri hat direction. That's weird, very weird, and it's usually kind of hard to do, but there are some tricks to kind of simplify that. What about a line charge? A line charge would be like a line with charge, and you have a part of it that's a differential charge length, and we can from that calculate the electric field at point R as being K, and then it's the integral over, this is a charge density because it's Q over L, total charge Q. Sometimes if you're talking about total charge, you make it a big Q. Lambda dL is the differential charge contained in that little segment right there. And so you integrate over each little segment as you go from R minus let's put it like this. Let's just say that this is my origin and this charge happens to be here at Ri, okay? And I'm calculating the field out here at R. Well, that'll be R minus Ri squared, okay? And again, in this direction. Let me just call that big R. That'll make things a little bit easier. Big R is equal to R minus Ri. And then I can say big R hat. In fact, I could write this as K integral of lambda dL over R, big R, squared R hat. And so that's fine. That's more like what you see it in your in the OpenStax book. In fact, I'll write it like this. But the key thing is there, you got to be careful that you are using the right R's. Okay, so that R that I'm using there is the distance from the charge location to the point where you're measuring the electric field. Okay. Now we can talk about a surface charge. So we have a surface here, a two-dimensional surface, and we take a little chunk out of that. The surface has a charge density sigma, which is equal to the charge per unit area. And so we say that the electric field at point R would be equal to K, and then we'd integrate over the surface charge, sigma dA, over big R squared times big R hat, again using the same kind of formalism. And then we could also think about a volumetric charge distribution where you have rho is equal to charge per unit volume, and the electric field will be K integral rho dV over R squared R hat. So that's just kind of the different ways to do that. Let's look at a quick example of how you would do that with, let's say, a line segment. Okay, so this is example 5.5 in the book. It says find the electric field at distance z above the midpoint of a straight line segment of length L that carries a uniform line charge density lambda. Okay, so we have a line of charge here like this. Total length is L, and I want to know the electric field right above the midpoint of this point. So I'm going to put it along an X, and they use a Z axis here. We're trying to judge the electric field here. And so they say, okay, let's consider these line segments here from little individual segments where you have a differential charge equal to lambda dl. Okay, the dl is the length of that segment, and that segment is located at position x along my x-axis. Of course, the length of my thing is L over 2 this way and minus L over 2 this way. So they say, you know, this can be a little bit easier if we think about, okay, what does this look like from, if we kind of back up a little bit. And so they say, look at these two segments that are on the opposite sides of the axis. Looks like I didn't quite get this in the middle, so I'm going to try to move it. Yeah, that's better. So if I have a differential charge here, if I make that small enough, it looks kind of like a point charge, right? And we know what the electric field of a point charge does. It points radially away from there. So if I call this dq1, then E1, oh, they call it 2. I'm going to stick it with them. So this is 2. E2 is pointing radially away from this differential line of charge, like that. Same thing over here with this dq1, which is also lambda dl, and it's located at negative x. Okay, it has an electric field pointing in this way given by E1, and maybe you can see that there's some symmetry involved here. If I'm looking for the electric field exactly at the midpoint, the x components of those fields really should cancel out. We feel like they should cancel out, and so we should just have a y component to the electric field at the midpoint above this line of charge. So, yeah, I'm just making sure I'm recording. I'm not hearing a lot of noise. That's good, I guess. Okay, so then how do I do this? Well, up here we said that the electric field at point R is equal to K integral lambda dl over R squared R hat. Now let's make sure we understand what all those things are. All right, the lambda is given, and it's a uniform charge density, so that actually we'll be able to take that out of the of consideration. We can pull it outside the integral, k lambda, and then it's the integral of dl r squared r hat. Okay, so if we look at what those fields look like, then okay, what's the r hat? Okay, and 1 second. Okay, so the dl is just dx in both of these cases, lambda dx. And so we're looking at integrating over the length of this line charge. But if we say, okay, whenever we do, let's say the right side integration, whenever we do this one, that's giving us this electric field. But if we consider that by doing this one, we could also calculate this one because there's going to be symmetry. In other words, every time we do this calculation, we might as well just include the other calculation because we can argue by symmetry that these electric fields have the same strength. They only have different y or z directions, right? So if we look at the x components, okay, let's look at E2x. Yeah, okay, E1x, it doesn't matter. That's going to be E1, and then they call this angle here theta. Okay, that happens to be, let's see, make sure that that's what they're calling theta. Yeah, theta, right. Okay, so if theta is that angle there, then this angle here would be 90 minus theta. Okay, this angle here is also theta. So E1, the x component of E1, that's opposite the angle theta. That would be E1 sine theta. Okay, and E1z would be the component adjacent to the angle, so E1 cosine theta. E2x is going to be minus E2 sine theta, and E2z is going to be E2 cosine theta. So what we notice here is that since E1 and E2 have identical magnitudes at this point, so E1 would be equal to k lambda, let's call it dE1, okay? The differential segment from that charge would be k lambda, we could use dx or dl, doesn't matter, over this r squared, okay? And again, I'm only worried about magnitudes. dE2 is k lambda, the same dx, over r squared, and it's the same r. And so these are actually equal. Therefore, the magnitudes E1 and E2 are equal. So the electric field, which would be E1x plus E2x I hat plus E1z plus E2z k hat, that one is going to go to 0. And so what I have is that the electric field is going to be E1z plus E2z k hat. All right? And I already know that those z components have the cosine in them. So the electric field is equal to E1 cosine theta. And in fact, I can just do it like this. Since E1 and E2 are equal, it's going to be equal to 2 E1 cosine theta k hat. Okay? Now the E1, that's the, I'm saying E1, I'm going to use E2 because I actually want to integrate from 0 to L over 2. And so, but you know, you could use E1, it's just the way that they chose E1 to be from the left side, E2 to be from the right side. I'm going to use the one from the right side. So The electric field at point P will be what we get if we integrate lambda dx over r squared, and then and that's the magnitude of E1 or E2, either one, cosine theta k hat times 2, because it's 2E1. So then I'll just put the 2 out here. 2 times k. Alright? And the integral that I'm doing is from x equals 0 to x equals L over 2. And I only have to do that once because this accounts for the negative side of the integral as well as the positive side of the integral. So yeah, so what I've got then is just that. Now, I do need to be careful about some of these variables that don't seem to relate to the integration variable, but they actually do. For instance, what is r? So the r is the distance. Oops, I'm erasing. We need to do that. R is this distance here. And if we look at what r is, x and z, the height where I'm evaluating this, r is actually x squared plus z squared to the 1/2. Okay? Furthermore, theta also depends on x. So remember, we're looking for any possible dependence in the integration variable. And r does, it has an x in it, but so does theta. The cosine of theta, if I look at theta, in fact, I kind of did it a minute ago. The cosine of theta is, let's see, it's this angle right here, which makes it this angle right here, which means that it is the adjacent z over the hypotenuse r. So the cosine of theta is actually equal to z over r, which is z over x squared plus z squared to the 1/2. Now if I put that into my electric field equation, okay, 2k lambda, it comes out actually, and I've got the integral of dx from 0 to L over 2 over x squared plus z squared to the 1/2, and then the cosine z over x squared plus z squared to the 1/2. Whoops, this one is not to the 1/2. This one is just to the 1 because it's r squared. And then in the k hat direction. Cool. Well, now I can do it. 2k lambda integral from x equals 0 to L over 2. The z actually can come out. It doesn't depend on x. So I've got the integral of 1 over x squared plus z squared to the 3/2 k hat. And there's a dx in there somewhere on this dx. I think that's it. So that's an integral that I can look up. Probably ought to know off the top of my head what it is. 2k lambda z. This integral ends up giving you x over, I'm just looking it up, z squared to the square times the square root of z squared plus x squared, and that's evaluated from x equals 0 to L over 2 k hat. Now, again, this only worked because I had symmetry. If I didn't have symmetry, I would have to go ahead and integrate the whole big thing. That's no problem. There will be examples where we do that, but not too concerned about that. So let's keep going. Okay, so L over 2, putting in L over 2 for x, z squared plus L over 2, L squared over 4 actually, to the 1/2, and then minus 0, oh, this is going to be 0, isn't it? So just like that, minus 0 over stuff. Yeah, so keep going. 2k lambda z. The L over 2, that'll cancel that out, so I don't have to worry about that 2. Put an L in there. Over. Okay, and then I've got, well, this z cancels this one, so I actually don't have to write that z. I've got one z down here, and then I've got z squared plus L squared over 4 to the 1/2 k hat. And that's, I think, about as simple as that expression can get. So that would be the electric field from a continuous line charge distribution. So they continue on in the book. They have an example with the electric field of an infinite line charge. They do a ring of charge, which is very important to look at because you've got some homework problems like that. And they've got the field of a disk, all excellent equations. One more that I want to look at, and that is the field of two infinite planes. The reason that I want to pick this one out specifically is because this is going to show up plenty. So we want to make sure we understand this. So here we have two planes, two infinite planes with opposite charges. The electric field lines from this will originate from the plus and end on the negative. Now, I haven't really said anything yet in the videos about this electric field line rules. That's probably the last video I'll do. But I just want to point out they use the result of the electric field from an infinite plane. Okay? That they got from doing the field of a disk. And so electric field of an infinite plane of charge. And this comes from, it's like this, sigma over 2 epsilon 0 in the k hat direction. This is a plane of charge that looks like this, and it's in the xy plane. You're looking for the electric field in the z hat direction, or the electric field is in the z hat direction. And again, this comes out of example 5.8, where they're looking at the field of a disk. So if you have two infinite planes, it's one of the really nice things about electric fields is that you can use superposition, okay, to calculate the electric fields. So here's the thing: plus is an infinite plane of charge. I'd have electric fields over here and over here that look like that, and the electric field is plus sigma over 2 epsilon naught, where sigma is the charge per unit area. If I have a sheet of negative charges, well, the electric field is minus sigma over 2 epsilon naught, and over here the charges point inward toward the thing, and over here they point inward toward the thing. Notice the thing about these electric fields is that they do not fall off as with distance. Because it's an infinite sheet of charge, an infinite plane of charge, the electric fields are constant everywhere. Well, that means if you bring these things together, then the electric field lines, let me draw these a little bit differently. The electric field lines from the plus, I'll make those red. I think I'm making it red. The electric field lines from the plus are red, right, like this. And the electric field lines from the negatives are blue, and they look like this. And maybe you see what's happening here. Actually, I need to extend my red a little bit, and I need to extend my blue a little bit, because you see that in these regions outside of the charges, the red point opposite the blue. But in the region in between the two planes, the red and the blue point in the same direction. And what that means is that here the electric field is 0, here the electric field is 0, but here the electric field is sigma 2 epsilon naught plus sigma over 2 epsilon naught. And so the electric field in this region in between the planes is sigma over epsilon naught. And let's just say that we made this the x direction, okay, and z, y, whatever. Then I would say that the electric field in between those regions is sigma over epsilon naught I hat. And that's a result that's quite important. We'll see that over and over again. So this is a device, I'm going to go ahead and name it parallel plate capacitor, is equal to sigma over, no 2, sigma over epsilon naught. And it's in the direction that is between the two plates. All right.